Hello, I am Yigit Erginbas, and today I'm going to present you my work, Interactive Learning with Pricing for Optimal and Stable Allocations in Markets. This is a joint work with Soham Phade and Kannan Ramchandran. Our goal in this project is to develop a framework for large-scale online recommendation systems, and here we integrate techniques from combinatorial bandits, optimal resource allocation, and collaborative filtering. Our main goal in here will be to design an online algorithm that is guaranteed to achieve maximal social welfare on one hand, while also achieving maximal stability in the market. As an overview of the system that we are considering, the system consists of a provider, which is going to employ an algorithm that's going to be developed by us, a set of users denoted by calligraphic N of size N, and a set of items I of size M. The system operates in multiple allocation rounds, indexed from 1 through capital T, and each user has a time-varying demand dt at each time, and each item has a time-varying capacity ct at each time. Demand and capacities limit the amount of different items or users that can be assigned to each different user or item. Each allocation, which is a mapping of a user to an item, results in an independent random reward. So when a user U is allocated with item I, the system obtains a random reward RUIT, whose mean is going to be given by theta UI. And to use ideas from collaborative filtering and to be able to capture the correlation between different user item pairs, we assume that the mean reward from each user item pair is given as the inner product of two feature vectors, where one feature is given by the user side and other part is the features of the item. So as their inner product, we have the theta UI, which is the mean of the reward that we obtain at each time from a user item allocation UI. And importantly, the reward distributions are unknown to the provider, which means the provider does not have any access to the distributions of these RUI random variables or its mean. In each allocation round, the system operates in three different stages. In the first stage, the provider decides on offers and prices, which is going to be applied to the system. Second part is where the users accept or reject their offers based on the prices. And third part is where the users send their feedback about the offered items. The first part, where the provider decides on offers and prices, can be represented by a selection of offers, xt, from a calligraphic set xt, that denotes the possible set of allocations that are valid according to the demand and capacity constraints. So the first part here, x times all ones vector being less than dt, represents the demand constraint, and x transpose times 1 being less than ct element-wise represents the capacity constraints. And provider also decides on prices for each item. So on the right figure, we see that we can represent the offer xt matrix by coloring the ones and zeros in different colors. And darker color means ones in this picture. And as we can see, the capacity and demand constraints limit the amount of different ones that can be found in each row and each column. So the capacity constraints limit the rows and the demand constraints limit the columns. Then, based on the offers that they have obtained and the prices for the items of their offers, the users accept or reject their offers. So if theta UI, the valuation of this U user for item I, is larger than the price of item I, then the user accepts the item, and it results in a positive reward for the system, for the provider. If the theta UI value, the reward value, is less than the price pi, then the user does not accept the item, it rejects, and it results in zero reward. And lastly, after deciding on accepting or rejecting, the users send feedback about the offered items, and the feedback they send is in the form of the rewards, RUI, and the expectation, as we described, is given by theta UI. In this project, we have two different design objectives. The first one is a common one, which can be found in many different papers in the literature, which is to maximize social welfare, which measures the total satisfaction in the system as a whole, which captures the satisfaction of both the users and items, or the provider, and to be able to measure how well we are doing in terms of social welfare, we are going to minimize a metric which we are going to define and call social welfare regret. On top of that, we also want to care about how each user thinks about the allocations that we make. So we also try to capture the user's incentives to conform with recommended allocations. And we define this concept to be the stability concept. And to achieve our goals, we are going to measure the metric that we are going to define and call instability. To begin with, the social welfare is defined to be the total amount of utility that the users obtain from allocated items. So it can be represented by the inner product of this X matrix, the allocation matrix, and the mean reward matrix theta, whose entries are theta UI values that we have defined previously. And to maximize the social welfare, it's an easy problem. It's an easy integer problem where we are maximizing over all different allocations that are valid with respect to the constraints, demand and capacity constraints. And we know that the solution for this problem can be obtained using the relax problem by relaxing the integer constraints into interval constraints. And because the integrality gap of this relaxation is 1, it means that the solutions that we obtain from the relaxed linear program are also going to be solutions for the original the integer program. On the other hand, we measure stability in this way. To define stability, we will start with the surplus, which measures essentially the happiness of each user from each allocation under some pricing. If the user is allocated X and under pricing P, psi function is going to give us how happy they are or the surplus that they have obtained. Then we say that a user is stable if under current pricing, the allocation that they are given XU offers the maximum gains among all possible different allocations that are valid with respect to their own demand constraints. So if XU belongs to this maximizing set of this psi function, the surplus function, it is going to be a stable allocation under this current pricing. If this condition is satisfied for all different users, then we say the whole allocation, capital X, with some prices P is stable. A fundamental property of this market model states that if the allocation and prices are selected as the primal and dual optimal variables of the relaxed allocation problem, which is this problem, then the market outcome becomes both optimal and stable simultaneously. To see this, we can consider the Lagrangian, the partial Lagrangian, because we're only converting the capacity constraints, and the corresponding dual optimization problem, but details are left for readers to check in the paper. And due to LP duality, the primal dual optimal solution satisfies the optimality and stability conditions. To formulate the problem, we go in this way. We know that the mean reward matrix is unknown to the provider, so it cannot directly solve the allocation and pricing problem as given. It needs to learn the mean rewards of the users for each different item, at least the ones that is important. So we need to consider an online framework that can learn the user preferences while achieving some guarantees about the regret. To define our metrics of regret, we go this way. We measure suboptimality in terms of social welfare regret. So we subtract the social welfare we obtained, the W of XT, from the maximum social welfare we could have obtained at this round. And to measure per user instability, we use surplus regret, which we define as the surplus that this user currently obtains, subtracted from the surplus that this user could have obtained from any allocation under the current pricing. So if we were to sum up the social welfare regret from first round to the last round, we end up with a cumulative metric, which we call social welfare regret. And our goal here is going to be to minimize the social welfare regret. On the other hand, we also define instability regret to be the summation of all different users' instabilities from time 1 to capital T, and our goal in here will be to minimize instability regret. However, importantly, our goal is not to minimize social welfare regret or instability regret on its own, but to achieve both minimizations simultaneously. So up to this point, we didn't discuss whether users can accept or reject offered items based on their valuations and prices, and we were assuming that all users are accepting the items that they are given regardless of the prices. However, if we want to introduce some mechanism for users to be able to accept or reject the offers, we can state that a user U accepts item I if and only if the valuation that it's going to obtain is larger than the price it needs to pay for it. So this condition gives us the mechanism for acceptance and rejections. So accordingly, if we were to modify our definitions of social welfare and surplus, we can achieve representation of the ability of users to accept or reject. To facilitate our analysis, we need to start with some assumptions. The first one is going to be that the rewards are independent and sub-Gaussian. And second assumption is going to state that the mean rewards of the users for different items is going to be given as the inner product of feature vectors fu and phi I. We start with the contextual case, where the item features are known as contextual information to the provider, and the user features are unknown. In this scenario, we know that the true theta matrix, the mean reward matrix, belongs to this set calligraphic F. So we can base our knowledge on this set, and we follow the standard optimism in the face of uncertainty principle in developing our algorithm. The OFU algorithm maintains a confidence set that is going to include the true value of theta with high probability, and it's going to be constructed as a norm ball for some norm that we're going to define, which we call empirical L2 comma infinity norm, and it is going to be useful in deciding on the offers that we are going to make, and as well as the prices. The algorithm chooses the allocation at each time by maximizing both the allocation and the parameter theta over the set xt cross ct. It maximizes the allocation among the allocations that are valid, while it also maximizes the parameter theta within the confidence set that we have currently, ct. Then, having obtained xt and theta t, it constructs its pricing strategy based on a value that we call p bar t, which is the optimum dual variable for the problem parameterized at the point theta t, where the theta t is the parameter that is found by the OFU step in the previous line. This is the general structure of the algorithm. The algorithm starts by finding a regularized least squares estimate of the parameter theta t, which we call theta hat t. Then it constructs the confidence set around that point using the L2 comma infinity norm, which is given by this form. Then it computes the OFU allocation, as we described previously, and it computes the prices p bar t, and instead of offering the items at p bar t price, the optimum dual prices right away, it subtracts an amount which is defined to be nu times square root of w to achieve that most of the items are guaranteed to be accepted. So the wt term here accounts for the uncertainty that we have for different items, and as time progresses, because the number of times that an item is going to be given to a user is going to increase, the wt term shrinks down, so the p bar t becomes much closer to pt. And we offer the allocation xt together with prices pt at the end of the day at each round, and observe the reward for all different user item pairs that we have allocated. One important thing to note here about the confidence set is it is wider in directions that are not yet well explored because of the definition of L2 comma infinity norm. So OFU step is more inclined to allocate those user item pairs that are not yet well explored. At the end of the day, we end up with some theoretical result, which looks like this. But importantly, it means that with correct selection of parameters, our algorithm can simultaneously achieve this order of social welfare regret as well as the same order of instability regret. One important thing to note about this order is that it is sublinear in t, which means that on average the amount of regret that we incur goes to zero as time progresses, as our horizon increases. As on top of that, it is sublinear in number of users. It is also sublinear in number of items. And this result holds for the case where the users are allowed to accept or reject. If you were to not allow them to reject, if you were to force them to accept all the offers that we are making to them, we can achieve a better result because the problem is easier, and it's going to be square root of t order for the number of rounds. Next, we continue with the case where we consider the item features and the user features to be both unknown. In this case, we know that the mean reward matrix belongs to the set of low rank matrices. As a result, we now consider confidence sets of the form as given. Now here instead of having L2 comma infinity norm, we use L2 norm right away, and our confidence parameter is given a different form. But in general, at a high level, the algorithm works in a similar way, only by replacing the confidence set to be now instead given by this Qt form. So with the correct selection of parameters in the low rank setting, our algorithm can simultaneously achieve this amounts of social welfare regret and instability regret. We note that this regret amount is still sublinear in t with order 3/4, and it means that on average we achieve no regret. So and as an additional remark, if the users are not allowed to reject, then we can also achieve square root t regret. Lastly, we have run some experiments both with synthetic and real-world data sets, and we have shown that our algorithm can perform better than some baseline algorithms. We have used two synthetic data sets in this figure, and the third column represents the movie lens data set, and the fourth column is for the Yelp data set. The first row represents social welfare reward. We see that we can achieve the maximum amount of social welfare reward with diminishing regret, and also we can achieve diminishing instability as time progresses, while some of the other algorithms are stuck with higher instability levels or much slower in achieving lower instability. Thank you for listening to me.